T being finite, right? That's what I proved. And lastly, the last step that I stopped for step 4 is the fact that ST is equal to the value of S1, which is 0, implying what was that? The value of ST is either negative A, ST being negative A, plus B, ST being B, and this is 0, implying, so this is negative A times a T plus B times 4 minus T, implying P probability that the random walk will hit negative A is B over A plus B. Okay. Okay, so this is what I did so far. And step 6 is this. Sorry. Expected value of T. Okay, so how do we do this? So we just have to we invoke the same the theorem on the wedge, the minimum T and between T and N. So from step 2, right? Again, so step 2 tells me that expected value of S squared T mean N is equal to minus T mean N. This is equal to expected value of S squared, 0 minus 0, which is obviously 0, of course. Okay. And then, so now we can split to bring, say, the T mean N to the other side. That tells me this. T mean N is equal to expected value of T. Okay. So it's very tempting up to this point to get rid of the N, so that you have S squared T being expected value of T. But the issue is we don't have enough knowledge, enough tool to do that. So we have to do this by hand. So basically the claim here is the following. T is expected value. Okay. Is it good? The issue is you cannot really employ the theorem. That's the issue. This is because so note that we cannot really employ the theorem, the last theorem, because S T mean S squared minus T mean N. This is not less than anything. Alright? And that is the issue. So we cannot really do this. We do have a more advanced theorem for this, but I guess for the sake of the course, let's do this by hand. Okay. So I think it's got okay here. Anyway, so what did I want to do? Okay, so now what do I have? So note that following. So the first thing is we're going to take n to infinity on this quantity. All right. Expect the value of T mean N. Okay. T mean N. All right. So I hope you still remember this formula. That is the summation of the probability. T mean N is greater than little k starting from 1 to 2. have a, you know, discrete random variable on the natural number, then that is just how I write the effect value. Okay, but the key here is this is always bounded above by m. So where did this sum go? So how far in the series? How far could the series go? Of course, I mean technically k running from 1 to infinity. Actually it just stop, it will just stop at n. So see this? Alright. Summation k from n plus 1. Okay. Ability teaming and alright. So to think about it, if the index k here is greater than starting from n plus 1, what is this probability? It will be 0, because think about it. Probability t mean n greater than n plus 1. Is it possible? That is impossible because this is always less than n. Right? And so this random variable cannot be bigger than this. So this has to be 0. And so technically you don't have so you don't have this sum. Right? In other words, you only stop right here. Okay, from 1 to n. T mean n. Alright. Okay. Alright. So then next. And so the next thing is, so if k is less than n, right? So now if, for instance, t mean n, for instance, say n minus 1, let's say. Okay. So the minimum between these two numbers is greater than this. What does it tell me concerning the t?
That t is greater than
T is supposed to be greater than this. But because the n is already greater than this, and so this is the same thing as t greater than n minus 1. Is the same thing? Okay. Because as you can see, this is basically the same thing as saying t greater than n minus 1 intersecting with n is greater than n minus 1. Alright? However, this event here is trivial. That is trivial. So this is the same as that. And so that the finite sum is basically the following. T greater than n. Alright? Okay, so now if I take n to infinity, basically I have t mean n, this expected value, is going to the infinite sum. So what is that limit? What is that series?
expected value of t.
The mean of t. So that is just the mean of t. Alright? So, as you can see, starting from this equation, I take n to infinity of the right hand side, I get the mean of t. And so the last thing is to take n to infinity over here. Right? And if I take n to infinity on the left hand side, I will get this. So that is one step. So another, the second step is to consider this. So consider the S square. So what do I have to say? So I have, so this is the type where you do T mean N. This is equal to respective value of S squared T, together with the fact that T less than N, plus respective value of S squared T mean N, T greater than N. Alright? If the T is less than N, then the minimum is T. On the other hand, if T is greater than N, I keep the wedge, I keep the minimum. And so next, this term here, the first term can be written further as the mean of ST squared, subtracting the mean of ST squared with ST, and then add back the second term to A. Alright. This is because the mean of the S squared at the time T can be split as into two pieces. One piece is when T less than N, and the other piece is when T is greater than N. So, okay. This is the term when, you know, when you have T less than N, T greater than N. And so here, the mean of so for any x here, right? X T less than N plus the mean of x to T greater than N, basically. Right. Okay. So what do I have? So that would imply if I bring the mean of ST squared to the left hand side. So this, right? If I bring it to the left hand side, I am left where, and maybe take the expected value. This, right? That will be less than by the triangle inequality for absolute value. I have ST squared, T greater than N, and ST mean N squared, T greater than N. Okay? So, now what can I say about this? So of course here the goal here is to try to show that this difference is going to zero. Alright, that's what I want to prove. I want to prove that difference is going to zero if I take n to infinity. And so I am drafting this difference by these two terms, but this is less than the maximum of A squared and B squared. And the same thing over here. A squared, B squared. Right? And so that's why the right hand side here is basically valued both by A squared, B squared. To bring that term outside, and I have the probability of T greater than. Of course, you have to do 2. Okay. Yeah. And now taking n to infinity, this is going to 0, right? So this, and we know this going to 0. And so the difference here is going to 0, and so we get what we need. So indicating expected value of s squared t mean n is going to expected value of s t squared as n going to infinity. Okay. Well, so that's why we prove the claim. We have the claim over here. So now, once we have the claim, computing the mean of t is pretty straightforward now, because of this, right? So let me keep this. Let me keep that. So now. The mean of t is the mean of st squared, and then it's just minus a squared, right? Probability st being minus a, and plus b squared, probability st being b. But then we know the first probability is b over a plus b. So basically I have a squared times b over a plus b, and then a plus b squared times the complement, which is a over a plus b, and the answer will be a times b. Just pull out the common term a times b. So remaining inside, just the sum is 1. Okay. Question? Thought? So let me move on to the last piece of the course, 5.5, the conversion. All right, so here's the deal. Suppose, I guess maybe let me write up here. Okay. So the last piece is if mn is non-negative, okay? If mn is a martingale and it is non-negative random variable, then it needs to have a limit. Then mn must have a limit as n goes to infinity. And the mean of and infinity, this random variable is the mean of this random variable is the same as the mean of it. Okay. So the key word here is a martingale. It has to be non-negative. If a martingale, if we take like a negative value, then we don't have such a limit. Think about like the random walk here. So the random walk, the S of t, S of n here is a martingale one, it could take negative value. And so it doesn't have a limit. But if it is, if you know it is non-negative, then you need to have a limit. Right? And so in other words, you should say, okay, this a random variable is multiplied infinity such that and then going to infinity is equal to 1. Alright. Okay. So last theorem of the course. Okay. So to explain, to illustrate the theorem, I'm going to skip the proof. It is actually an advanced argument, and it's not really easy. So let me skip that. Let me discuss the problem. Example. Polynomial problem. All right. So suppose I have at the beginning. All right. The Earth has say R rect, and minus R blue. Okay. At the beginning, in the Earth, I have a number of the red balls and a number of blue balls. I mean, the number of the red is R, and the number of the blue is n minus R. In other words, the total is n. Okay. All right. So now I'm gonna pick a ball randomly. Pick a ball randomly, and add a ball. So I guess I want to say add one more ball of the same color to the other. Okay. In other words, I will pick a ball randomly. If that chosen one is red, I will add another red to the other. And likewise, if I pick up a blue, I will add another blue to the other. Alright. Okay. So what next here? So let me denote by R sub K to be the number of the reds after K after time K numbers. I don't know. After time. Okay. Alright. Of course, the R naught at time 0 is just a little R. Right? So R naught is just a little R at the beginning. And so this RK here is just a Markov chain, basically. Because in order to determine the nest, number of the red in the urn, I just have to base on the current number of red. Alright. And I'm going to denote M sub K to be the ratio of the red, namely, so the ratio is the ratio of red after time K. Alright. And so note that NK is just RK divided by the total balls after time K. And why is that? How many balls total? N plus K. Right. So after K times, I have a total N plus K. Right. So the claim is this is a Martin gap. Alright, so plan is, so number one, MK is a Martin gap. Of course, the ratio MK is simply a non-negative random variable. Right? It's non-negative, obviously, and it's a Martin gap. Okay. So to see this, it's pretty intuitive because think about the RK first. So RK plus 1, all right, condition down RK. Okay. But roughly speaking, it goes like this. If I have this number of rent at the time k, then what could I have in the next step? So either the number of the rent stays the same with the probability 1. So think about it. Right? So this is the number of the rent at the time k, and the other one, the other is the blue and plus k minus 1. Okay? So how is it possible that the number of the rent will stay the same after this k plus 1 draw? It stays the same if I pick out blue. Right? If I pick out blue, that means that probability will be basically 1 minus RK over N plus K. Okay. Yeah. And I will increase one more rank if I pick out a rank. So really RK over N plus K. Alright. Yeah. I mean just a Markov chain basically. The number of the rank is determined at the number of the red at the moment. So basically that's what it is. Okay. So now we check the M, the ratio is in martingale. So I guess a couple of ways to do this. Let me do the following. So, M k plus 1, conditioned on the past. So I guess let me call it to be, let's say big RK is the little RK. Okay? Alright. So this is what it is. This is okay, so by the definition, that is RK plus 1, condition down N plus K plus 1, sorry, over N plus K plus 1, right? At the time K plus 1, this is, the numerator is the total balls that I have at the time K plus 1. And so, okay, so value on this, condition on this trajectory. And so, okay, so bring out the numerator. Sorry, the denominator. The denominator is a constant. I will bring that out. Plus k plus 1. RK plus 1. Conditioned on RK is the real RK. Whatever here. Right. And then we just have to follow the observation that we have over there. So this is equal to either I have RK with the probability 1 minus RK, little RK over N plus K, or I increase one more ball with the probability RK over N plus K. Alright? Yeah? So, alright, so allow me to skip algebra, but basically over here, after simplification, we will end up with, I'm pretty sure, we will end up with RK over N plus K, alright? And what is this? That is just exactly NK conditioned on RK equal to RK. That'll be the factor. All this way. And so NK is just a margin. Is there any question about margin stuff? No? Okay, so we have the MKE and the martingale. So now, what happens if I take case infinity? All right. And so for the sake of simplicity, so let me mention a particular case that they discussed in the book. Right, so part number 2. Now suppose at the beginning, I only have one red and one blue. So at the beginning, only one red and one blue. So n is equal to 2 or is blue. Okay, just a very simple case. At the beginning, I have 2 balls, one red and one blue. Okay, so the claim is then and then going to uniform, I guess, infinity, which is distributed as a uniform distribution in 0. Right? Okay. Of course, I know the limit. Random variable has to exist based on the theorem that I just mentioned here, right? So M infinity exists. But what is the distribution of it? And in this case, it is uniform in 0 and 1. Okay. So this piece here is just a theorem. The theorem here. But this is what we need to analyze. Alright. To see this. And so note that, what do we have? So the claim is MK is indeed uniform on the set, on the discrete set from 1 over n plus k up to so that will be k 1 plus k. So okay, so n is 2. Okay. In other words, for say j from 1 to 0 to k, the probability mk being 1 plus j 2 plus k is 1 over k plus 1. You think about it. So it is it's uniform in this. So I guess I have this is 1, 2 plus k, 2, 2 plus k, all the way up to 1 plus k over 2 plus k, and this is 1. This is 0, all right? And so this random variable is uniform on these discrete points. And so as you can see, if I take k to infinity, the number of discrete points will be, will get more denser. Yeah. So you can imagine like the mesh is going down to 0. And so if the mesh is going down to 0, then I have to approach the uniform between 0 and 1. That is is the intuition. Okay. Okay. Maybe just let me write down all the properties, because obviously I don't have much time for that. So the plan number one, so is this. Plan number two is now MK is going to, well, maybe for the sake of the math that you learned, let's just say this is going in distribution. All right. Okay. This will be employed by the NGF technique. So this is NGF technique that you have practiced in the homework. Right? Okay. Basically, I have to, compute the NGF of the MK, but then you see you have a Riemann sum, and that Riemann sum will convert to the NGF of the uniform. We call NGF of uniform, or maybe just let me do this. So maybe just accept this for the moment, all right? Let me do the claim number two. So static value of E, T, and MK. Okay. And if you look at this, well, you can compute immediately that the NGF of the MK is simply, well, this probability, right? So the summation 1 over k plus 1 times e to the t, 1 plus j over 2 plus k. J running from 0 to k. Right? Okay. And then, well, what is this stuff? So if you sketch it out in a graph like this, you realize this is basically a Riemann sum. So I have the mesh is 1 over k plus 1, so I have 0, k plus 1, 2 k plus 1, all the way up to this is k over k plus 1, and this is 1. Okay. All right. And this, the function here is well, so basically that kind of like the area of this rectangle. All right. And well, and so if you take the mesh down 0, in other words, taking k to infinity, then basically that the Riemann sum will have to convert to the integral. Okay. And what is that integral? So if I take k, the mesh to 0, then that we have to convert to the integral from 0 to 1. Okay. And I have e to the t, basically that would be like, basically that would be e to the tx. Yes. Okay. Is that true though? Well, it has to be. It has to go to that integral. I mean, right from the formula, it doesn't seem like so. Right from the formula, it doesn't seem like so. I mean, like, so if I think about this is being my, like, I don't know, this is my, Yes. So think about this is running from 0 to k. So I have, this is kind of like what? 1 over 2 plus k, 2 over 2 plus k, all the way up to the last piece here will be 1 plus k over 2 plus k. Right? Yeah. And so eventually that would have to go to, sorry, this is e to the t, my bad. E to the t here, and then e to the t. Sorry. So basically it has to go to e to the t. Basically. If you're not convinced, then try to fool it yourself. Okay? Anyways, but what is this though? This is the MGF of the uniform neuron. Okay? That is the key word though. The key word is this is the MGF of the uniform, and so you will need to have this. Okay, so I already ran out of time, so let me put the final remark. Is in general, if you have R and N, in general, then NK will have to convert to a beta distribution with parameter R and minus R. Okay. That is something to know in general. Okay. But if you have a particular case, R being 1 and being 2, then we have uniform, because uniform distribution is just a particular case of beta. Note that uniform 0 to 1 is just beta 1. Okay. All right.
I have a question.
Yes.
How much previous knowledge should we study for the final? In the sense of how many moment generating functions, distribution,